true projects. In this video, we are going to explain about the project entitled as Drawing Away Parkinson Disease Detection through Hierarchical Deep Learning Models. So before getting into the video, let me give you the brief description about the project. This title describes a system that detects Parkinson disease by analyzing drawing patterns made by individuals. It uses hypothetical deep learning models to capture both low-level drawing features and higher-level structural patterns. This approach aims to improve early and accurate diagnosis by leveraging subtle motor parameters reflected in drawing behavior. Coming to the abstract, this abstract explains the importance of early detection of Parkinson disease and highlights the limitations of traditional subjective diagnostic methods. It introduced an automated approach that uses patients drawing tasks to capture fine motor impairments associated with the disease. By applying hypothetical deep learning models, the system extracts meaningful features at multiple levels to accurately classify Parkinson disease. Overall, the study emphasized improved accuracy, robustness, and interpretability in PD diagnosis. Coming to the existing system of Parkinson disease detection largely rely on clinical evaluations, including motor assessment, patient interviews, and neurological examinations, which are subjective and time consuming. So, recent approaches incorporate machine learning techniques using handwriting and drawing analysis. But these methods often depend on handcrafted features and shallow models that cannot effectively capture complex spatial and temporal patterns in drawing data. As a result, their scalability is limited and they fail to provide a hypothetical understanding of disease progression, leading to reduced accuracy and sensitivity, particularly in the early stage of Parkinson disease. Coming to the proposed system or base paper work, the proposed system presents a hypothetical deep learning approach that automatically detects Parkinson disease using drawing tasks. It combines convolutional neural networks to extract detailed spatial features from drawing with recurrent neural networks to analyze temporal patterns in stroke movements, enabling the capture of suitable motor impairments. By learning from drawing samples of both Parkinson patients and healthy individuals, the system accurately distinguishes variance in stroke dynamics, pressure, and speed. This hypothetical design improves early detection accuracy, offers interpretable insights into motor deterioration, and ensures robustness and generalized for real-world clinical use. Coming to the data set, the hand PD augment data set from Kaggle is designed to support Parkinson disease detection through analysis of hand-drawn images. It contains drawing collected from both healthy individuals and PD patients, organized into two labeled classes, healthy and Parkinson. The dataset includes various motor assessment tasks such as spirals, waves, and circles, which reflects fine motor control. To improve models' performance and generalization, data augmentation techniques like rotation, scaling, translation, and flipping are applied, creating a more diverse training set. This structured and labeled data set enables effective training of deep learning models to identify subtle motor impairments associated with Parkinson disease. Coming to the novelty or extension or enhancement or improvement. Firstly, advanced deep learning architectures such as exception, NASNet large, and ensemble models were applied to improve classification accuracy, along with YOLO models to detect and localize abnormalities in drawing images. Next, explainable AI integration. GradCam was used to generate heat maps that highlights critical image regions influencing model predictions, improving transparency and interpretability. Along with that, user-friendly deployment. A Flask-based web interface was developed to enable Users to upload drawing images and receive Parkinson disease predictions from the trained models. Coming to the flow of the work, first, importing the packages. The workflow begins by importing all necessary Python libraries required for the project. This includes libraries for data manipulation, image processing, deep learning frameworks for model building and training, YOLO libraries for object detection, evaluation metrics for performance analysis, and the Flask framework for deployment that trained models as a web application. Next, data preparation. In this stage, drawing datasets related to Parkinson disease detection are collected, specifically circle, spiral, and Mendel drawings. To improve data diversity and model robustness, multiple augmented versions of these images are merged with the original datasets. This results in a comprehensive and balanced datasets for each drawing type, enable better learning of motor patterns. Next, pre-processing. The pre-processing step is divided into classification and detection tasks. For classification, image data augmentation techniques such as resizing image into 299 into 299, random horizontal flipping, rotation, and tensor conversion using torch transformations are applied to enhance generalization. For detection, all three drawing datasets are merged into a single dataset and a data.yaml file is created to define dataset paths and class names required for training YOLO models. Next, maintain parallel datasets. Two parallel datasets are maintained to support different learning tasks. The classification dataset consists of images paired with their corresponding class labels, while the YOLO dataset includes images with bounding box annotations. This separate ensures that both classification and detection models receive appropriately formatted inputs. Next, model training. Multiple models are trained to access performance and robustness. Classification models are trained using five-fold cross-validation, including baseline models, the proposed ResNet 18 and advanced extinction models such as exception, NASNet large, and their ensemble. In parallel, YOLO-based detection models are trained to localize and classify Parkinson-related abnormalities. Model performance is evaluated using standard metrics such as accuracy, precision, recall, F1 score. Confusion matrix for classification and MAB precision and recall for YOLO detection models. Next, interface pipeline. The final stage involves deploying the trained models using Flask-based web application. Users upload drawing images through a simple front-end interface, after which the backend processes the image by first running the YOLO models for detection and localization. The classification or ensemble model then predicts the Parkinson disease type. The results, including bounding boxes, predicted classes, and confidence scores, are displayed to the users, providing an intuitive and interactive diagnosis tools. The algorithms used in the project are ResNet 50, MobileNet V2, EfficientNet B0, ResNet 18, Exception, NASNet Large, and an ensemble technique which combines exception and NASNet. As an extension, we have applied YOLO-based detection models like YOLO V5, YOLO V8, YOLO V9, and YOLO V11. Coming to the requirements, we have both hardware requirements and software requirements. Hardware requirements consisting of operating systems, Windows only, processor i5 and above, RAM 8 GB and above, hard disk 25 GB and above. Software requirements consist of application framework is Anaconda, primary language is Python, front-end framework is Flask, backend is Jupyter Notebook, database is SQLite 3, technologies which we use to build the front-end are HTML, CSS, JavaScript and Bootstrap 4. To execute this project, first we need to open the code folder which contains the project source code files. This folder is a complete package of your project's code base containing everything needed to develop, test and deploy your application or model. Static folder. This folder consists of files related to CSS, JavaScript and Bootstrap. Templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represents different pages of the website. App.py file. This .py file contains the information related to front-end logic. It could include code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. IPYNB files. This is a Jupyter Notebook files which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute the code in individual cells, making it a popular choice for data science. Signup.db file. This file is a database file used to store the user information. Now, coming to the execution of the project, first, you need to copy the path of the code folder from the address bar of the file explorer. Then, open Anaconda prompt. Use the command cd followed by a space and paste the copied path. This command is used to change the current directory to the code folder's path. Now, compile the app.py file using the command python space app.py. This command will execute the Python script and perform a runtime check with any syntax errors or logical issues. After running the app.py file, the Flask framework will host an application locally at the default address with the port number of 5000. Copy the local link provided by the framework and paste it into any web browser. I prefer Chrome. So this is the homepage of the project should now be displayed in the browser. This is a front end built using Flask framework. In this page, we have home button and sign up button. Now click on sign up button so that the logon HTML will be opened. Here we need to give the details and create an account for user authentication like username, full name, mail ID, mobile number and a strong password. Then click on create an account so that all the given details are stored in signup.db and the login.html will be opened where we need to access the application by username and password. Now the prediction page has been displayed. In this we have prediction button, data visualization button, notebooks button and sign out button. Firstly click on prediction button so that the classification and detection are open. Firstly click on classification so that the uploading for drawing for classification will be open where you need to upload a patient's drawing for drawing aware Parkinson disease classification using hierarchical deep learning will be open. Here we need to select the model like circle. Then here we need to upload the image. The image must be in the format of JPG, PNG and GIF. Click on browse. Choose an input from the test cases classification as we have selected the model of circle, open circle, then healthy, just open it and click on analyze drawing so that the input image is pre-processed and the output will be displayed as the classification result is healthy. The original image is this and the heat map image is this. And we also have the classification probabilities like healthy is 100%, patient is 0%. We also have the recommendations and precautions. Then click on analyze another drawing. Again, this will be open. Select any one model. Then click on browse. Now choose from the patient. Then click on analyze drawing so that the input image is pre-processed and the output will be displayed as patient. The original image is this and the analysis heat map is this. Healthy is 0% and patient is 100%. So here we have the recommendations and precautions. As we have tested for classification, now let us check for detection. Here you need to browse from the code folder test cases, choose detection and choose any one of the image. Click on open, then click on analyze drawing so that the input is pre-processed and the output is displayed as a healthy image. The detection information is given here. Detection method which we have used is YOLO. Detection type is single stage object detection. Localization is bounding box detection. Processing speed is real time detection. Here we have the detection features like object detection, bounding boxes, and confidence score. Now click on View Analytics. Now click on Data Visualization. As we have taken the three different data for classification like circle, Mender data, and spiral data. These three are for classification graphs and these are for detection graphs. So let us check one by one. Circle data visualization graphs. In this, first we have confusion matrix graph. The confusion matrix shows excellent performance, correctly classifying 176 healthy and 153 patient cases. Only 3 patient cases were misclassified as healthy, with 0 healthy cases misclassified as patient. Next, we have accuracy graph. The bar chart compares accuracy across different ML models, showing all models achieve higher performance above 94%. The ensemble models attains the highest accuracy, slightly outperforming individual models like Exception and NASNet Large. Next, we have F1 score graph. The graph shows F1 score of different ML models, with all models demonstrating strong and consistent performance above 0.94%. The ensemble models achieve the highest F1 score, indicating the best balance between precision and recall. Next, we have recall by model graph. The bar chart illustrates recall values of different ML models, with all models achieving high recall above 94%. The ensemble model shows the highest recall, indicating superior ability to correctly identify positive cases. And next, we have precision graph. This graph compares precision across different ML models, showing consistently high precision values above 95%. The ensemble model achieves the highest precision, indicating the most accurate positive predictions among all models. Let us check with meander data visualization. In this, we have the confusion matrix. It shows the distribution of true positive, true negative, false positive, and false negatives of meander drawing classification. Next, we have F1 score graph. It represents the balanced performance of the model by combining precision and recall for meander data. Next, recall graph. It highlights the model's ability to correctly identify positive meander drawing cases. And finally, we have precision graph. It displays how accurately the model predicts positive classes in meander drawing analysis. And next, we have spiral data visualization. In this confusion matrix, it visualizes the true positives, true negatives, false positives, and false negative for spiral drawing classification. Next, accuracy graph. It shows the overall correctness of the classification model on spiral drawing data. Next, F1 score graph. It represents the harmonic mean of precision and recall for evaluating spiral data classification performance. Next, we have the recall graph. It indicates the model's ability to correctly identify positive cases in spiral drawing analysis. Next, we have precision graph. It displays the proportion of correctly predicted positive cases in spiral data classification. And now let us check the detection data visualization graphs. First, we have YOLO precision graph. This graph compares precision scores of different YOLO models, showing YOLO V8 achieving the highest precision. YOLO V11 has the lowest precision among the models, while YOLO V5 and YOLO V9 demonstrate strong and comparable performance. Next, we have YOLO recall graph. The graph compares recall values across different YOLO models, with YOLO V8 achieving the highest recall. YOLO V11 shows the lowest recall, while YOLO V5 and YOLO V9 maintain strong and balanced detection performance. And next we have YOLO MAP score graph. The graph compares MAP values of different YOLO models, with YOLO V8 achieving the highest mean average precision. YOLO V11 records the lowest MAP, while YOLO V5 and YOLO V9 show strong and competitive detection performance. Then click on sign out. So finally, this project demonstrates that drawing-based features combined with hierarchical deep learning models can efficiently support Parkinson's disease detection. The model successfully captured fine-grained motor impairments from drawing patterns, leading to highest accuracy and reliable performance. Ensemble and advanced deep learning architectures further enhance robustness and generalization. Overall, this approach shows strong potential as a non-invasive, cost-efficient tool for early Parkinson's disease screening. So this is all about your project. Thank you.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.